Of all the videos I have made, VPC configuration is by far the most popular, but I never really explained how VPC works. So now it's time to go back and have a look below the surface of VPC. Before we go on, please subscribe to be notified of any new videos or follow me on Twitter. A VPC is a special type of ether channel or lag. It connects a device to two switches, not just one. This is why it's part of the multi-chassis ether channel family. VPC is a Cisco technology found in the Nexus platform. It's a bit like VSS, which is also a Cisco technology, but for the Catalyst platform. Other vendors have similar technologies as well. There is no special requirement on the device end. As long as they support LACP, they'll be fine. The dual-active links help with increasing bandwidth and decreasing the need for spanning tree. When connecting switches with spanning tree, some links will be active while others will be disabled. VPC is an effective way to work around this. VPCs provide redundancy and dual-active paths. As there are two or more paths to two switches, there is no single point of failure. Even if one switch fails, traffic will still flow. Like Etherchannel, VPC is a Layer 2 technology. Frames may be sent over any link. Frames are not duplicated over links to both switches. As we'll see a bit later, this would be really bad. Let's start with a few basics. VPC uses two Nexus switches called peers. The two peers and their related components are collectively called a VPC domain. Each domain has a unique value called the domain ID. Each switch can only be in a single domain. One of the switches will be primary, and the other will be the secondary. Both switches forward traffic. The primary switch handles the majority of control plane traffic. VPC uses two special links to connect the two switches. These are the peer link and the keep alive link. The peer switches use the Layer 3 keep alive link for sending and receiving heartbeats. This is how one peer can see if the other peer is still alive. Some failures could cause a situation where both switches are up, but they cannot see each other. Both will think they are the primary switch, causing a split brain scenario. To prevent this, the keep alive link is isolated in a separate VRF. This gives each switch a unique way of seeing if the peer is up. A good option for a small network is to connect the management interfaces of the two switches. In a larger environment, the management interface may connect to the out-of-band management network. Another alternative is not to use the management interface at all, but use normal interfaces in a dedicated VRF. The peer link is critical. It's a high-speed link used for forwarding traffic and sharing state updates. It forms a sort of backplane between the two peers. The peer link forwards broadcast and multicast traffic. Under some conditions, such as a link failure, it will also carry regular unicast traffic as well. MAC addresses that the switches have learned are synchronized. By sharing this information, they can recover faster during a switch failure. In any switch with VPC, there are two types of host ports. These are member ports and orphan ports. A member port is any port that is configured with VPC, such as ports connected to a server. Any VLANs allowed on the member ports must also be allowed on the peer link. An orphan port is any port that has no VPC configuration. This is common for individual ports connected to routers. Any VLANs on these ports do not need to be on the peer link. VPC will check each member port for inconsistencies. If it finds a problem, it calls them a Type 1 or Type 2 inconsistency error. If a Type 1 error is found, the primary switch will keep the ports up, and the secondary switch will disable its port. This allows the traffic to continue to flow without causing errors. This type of error is common if some of the config doesn't match on both switches. A Type 2 error is less severe. Both switches will keep their ports up and will generate syslog messages. VPC is still very much like active Ether channel. Connected devices still use LACP to negotiate the lag. Yet with VPC, there's a catch. In a normal lag, each LACP device has a system ID. The system ID is used to make sure that there is only one device at each end of the lag. This is a problem for VPC, which uses two switches on the end of a lag, not just one. Nexus switches are able to work around this. They use the domain ID, which we configure, to generate the system MAC. They then use the system MAC to generate the system ID. When generating the system ID, LACP also uses the system priority. This means that the system priority also needs to be the same on both switches. With the same system ID, they now appear as a single switch to any connected device. The domain ID brings up an interesting point. What happens if you have several pairs of VPC switches in the network? To prevent problems from bad cabling, each pair should have a different domain ID, which results in a different system ID. Duplicate frames are a very bad thing. Imagine a scenario where server 1 is sending traffic to server 2. Server 1 sends frames to switch 1. What would happen if switch 1 forwarded the frames to switch 2 over the p-link? Both the switches would attempt to deliver the traffic. This can be annoying for some kinds of traffic, but could cause serious problems for others. The good news is that VPC won't allow this to happen. You see, VPC lives by a personal code. It goes something like this. If a frame is received on the p-link, and the frame needs to be delivered to a member port, the frame will be dropped. Let's think about the earlier scenario. Server 1 sends a frame. Switch 1 gets the frame and forwards it to server 2, and over the p-link to switch 2. Switch 2 gets the frame and realizes that it needs to go to a member port. Switch 2 recognizes that switch 1 will already have delivered the frame and will drop it. What if the traffic needs to be sent out an Orphan port? The duplicate frame prevention rule does not apply here, and switch 2 will not drop the traffic. VPC is very useful for limiting the negative effects of Spanning Tree. But that doesn't mean you should disable Spanning Tree entirely. Think for a moment about what would happen if other switches are connected to the VPC domain. If Spanning Tree were disabled, a loop could form. As you can see, Spanning Tree is critical. VPC switches can still run Spanning Tree. As you would expect, the VPC pair still appear as a single switch. By default, only the primary switch will send and process BPDUs. You can optimize this with the peer switch command, which allows both switches to take part in Spanning Tree. Even when they're both processing BPDUs, the VPC pair will still appear as a single switch. This is because they use the same bridge ID, and generally would use the same bridge priority. VPC is resilient, but it is not invincible. Member ports can go down, the p-link or keep alive can go down, or an entire switch could fail. It's time to take a look at what will happen during a failure. Let's start with failing member ports. This one's quite simple. If a member port fails, the second switch continues passing traffic. And of course, you'll get some messages in your syslog. What if an entire switch fails? This is also a pretty simple scenario. The alternate switch continues to forward traffic. Unless, of course, you have orphan ports. Orphan ports are only connected to a single switch anyway, so these devices will now be isolated. If the failed switch was the primary, the secondary will take over the primary role. What will happen when the switch has been restored? Will the failed switch become primary again? I'll give you a few seconds to think about this. So what do you think? VPC switches are not preemptive. This means that the restored switch will be the secondary and the other will remain as the primary. This happens because there is a risk of traffic loss when the switch transitions to the primary role. Now for some more tricky failures. The peer link is the most critical component of the VPC system. When the peer link fails, both switches are still able to see that the partner is up thanks to the keep alive link. This creates two problems: duplicate frames and loops. To handle this, the secondary switch shuts down its member ports. The primary switch continues to forward traffic as normal. Orphan ports also stay up. Let's make this a little more interesting. What happens if the primary switch fails now? This is a pretty unlucky scenario to be in. The secondary switch notices the failure when it misses heartbeats on the keep alive link. The secondary does its duty and takes over the primary role. Its member ports are enabled and traffic flows again. If the keep alive link fails, there will be no heartbeats. Pretty bad, right? Well, no, it's not as bad as it sounds. The peer link is still up, so the peers are still happy. Let's look at another rare scenario where both the keep alive and peer link fail. The first possibility is where the peer link fails first, and then the keep alive fails. This isn't too bad. The secondary has already disabled its member ports, so when the keep alive fails, there's no operational impact as only the primary is forwarding traffic anyway. Let's imagine that you're having a really bad day. First the keep alive fails. Not too bad so far. Then the peer link fails. Each switch thinks that the other switch has failed. The secondary switch does its duty and takes on the primary role. Both switches are now trying to forward traffic. This is called a split brain scenario. This is where you, as the administrator, need to intervene. While this is rare, it highlights the need to design the solution well. For example, use redundant physical links for the peer link. And that's the high-level explanation of how VPC works. You can get more detail in the full article on the Network Directions site. I'm also considering a short video on dynamic routing with VPC. If this is something you'd like to see, let me know in the comments below. Don't forget to subscribe, and thanks for watching.